Hello, those who are watching this in the future. I'm David, I'm the coordinator of the Maths Learning Centre here at the University of Adelaide. It's Semester 1, 2023, and this is a revision seminar for Statistical Practice I. All right, whoa. Okay, so I'm going to talk about ANOVA. How do people feel about ANOVA? Yep. So you're saying you're not sure when to use it because it feels similar to some of the other tests when there's multiple variables going on. Cool. That is a vibe in StatPrac 1 that you've got. There's about, 10 different tests, and it can be sometimes hard to tell which one to use when. That's the sort of thing that you're saying? Cool. I'll definitely talk about that then. So I'll just talk as what I understand about ANOVA, and hopefully we can make sense of it. So it's short for Analysis of Variance. And it was invented by, I can't remember what his name was, Ronald, I think, Fisher, in the 1930s. And he invented the word variance in order to give this a name. Fisher invented the word variance for the square of the standard deviation. There you go. He invented most of modern statistics up until the 1940s. And then he died of tuberculosis. It's very sad. After moving to Adelaide and catching pneumonia. So there you go. And it is designed to compare a numerical, in your course it's called a quantitative variable, across multiple different groups. That's what it's for. So I'm going to draw a picture. So the way analysis of variance works is that you've got some sort of situation, and it may be people, it may be schools, it may be countries, it may be days of the week, it might be it could be anything, because it's statistics, we're going to be using it for all sorts of things, but I like to draw people for it. And your individuals that are in your study, you're going to measure two things on them. You're going to measure some sort of number, and you're going to say what kind of group they're in. And the group is going to have various different categories, which I draw as boxes. And the people are going to be in different boxes. Maybe it'll be control and treatment 1 and treatment 2. Or maybe it will be, if they were chickens, like the high protein food and the high fiber food and whatever, And so there will be all different options for what the individuals are given. And then there'll be a number that you measure. And I'm going to draw this as a scale to measure the number on. The reason I'm doing this is that this is my way of processing what statistics procedures do. And the question that you're asking in ANOVA, your research question is you're interested in how this number is different for the different individuals. And you want to know whether being assigned a different group or just having a different group makes a difference to that number. That's the research question. So the research question is, does being in a different group make a difference to which number you get on average? And that is the research question. And also importantly, the individuals in your study, every one of those individuals is only in one group. They're in one group and they're not in two groups at the same time. The groups are made of different individuals. So I just want to compare that to some of the other things that we do in statistics. So you can compare it to the t-test. Now, does your lecturer call them, do they call it the two-sample t-test or the independent samples t-test? Two-sample t-test? So the two-sample t-test is this situation. There is a number and you're interested in whether being in a different group makes a difference to being in a different number, to having a different number, but there's only two groups in the two-sample t-test. But in ANOVA, there's more than two groups. That's one of the differences. So the t-test only goes for two groups only, and ANOVA goes to more than two groups. Technically, you can use ANOVA for two groups as well, but we've already got the t-test for that, and so people don't do that. And so it's really designed to do the same job that the t-test does, but with more groups, more than two groups. The other thing we could compare to is regression. And in regression, everybody's got a number to say how the number changes. So there's two numbers involved. So for example, maybe if these people, we were measuring their temperature, in this one, this is my classic example for ANOVA that I like to use, chili in the meal that you ate. Maybe these people have no chili and these people have chili powder and these people have chili flakes, right? Maybe instead of measuring the type of chili you have, you just say how many milligrams of chili powder were they given? And then you've got a raw number that everyone could have lots of different options for that number. And so the different people all have their own different numbers and there's lots of different options for what the number is. That is what regression is for. And it's extremely similar to ANOVA. Only there's just many, many options for what this number could be. Sometimes when people set up an ANOVA and they just have 0 and 5 grams and 10 grams, they treat them as different groups instead of treating it as a proper number. And maybe that's some of where the confusion comes from. So then the line is usually if there's lots of different numbers that people could have and you measure it as a decimal, then you use regression. But if there's just only 3 options, then most people use ANOVA for that. I hope that's helpful. Yeah. And last thing to compare to is the chi-squared test. We did chi-squared, didn't we? Right at the end. The chi-squared test also allows you to have multiple different groups here. But the thing that you measure right down about the individuals in the chi-squared is also a category. So every individual has a group that they're in, but they also have some other category that you're trying to measure. Maybe it's like when they have chili, what's their opinion of the meal? Do they like it or not like it, for example? That would be that sort of thing. If you would like to see more of me talking about this, if there's time I can do more of it later, but there's also several seminars online about this way of organising the information about your research situation that helps you choose what stats goes with it. So there you go, they're the main ones. I can't not do this. In the paired t-test, there is still a number that you're interested in, how it changes, and there's still 2 situations that the people are in. It's just that everybody is in both of these situations. Yeah. So there is actually technically a thing for ANOVA that has people a repeated, like a paired situation too, but you don't learn it in this course. And so one useful thing about trying to figure out what situations to use different tests in is to compare these pictures about how what variables are measured on and which ones go with which people to see how they're similar and how they're different. So I can see that ANOVA is very similar to the t-test. The only thing that's different is the number of groups. And it's very similar to the chi-squared test. The difference is that the chi-squared has a category as the outcome and then the ANOVA has a number as the outcome. Sorry, categorical variable and quantitative variable. Sorry, I should use the real terminologies. And that's one of the reasons they spent such a lot of effort talking about quantitative and categorical variables in the first week of the course, is because that information is what you need to decide, one of the things you need to decide between which test goes with what. How are we feeling? Cool. So that's what it's for. It's for this situation where your research question is set up that way. And just the last thing to add is your data will look like this. And there'll be like a column for which individual it is. And there'll be a column for the group, and there'll be a column for the number. And there'll be person 1 is in group A and they have this number, and person 2 is in group A and they have this number, and person 3 is in group B and they have this number, and person 4 is in group B and they have this number, and so on, right? It'll look something like that. That's what the data looks like. A lot of people, when they collect data, do not set it up this way. What they normally do is they have group A and they have all the numbers that go with group A, and then next to it group B and all the numbers that go with group B, and then next to that all group C and all the numbers that go with group C. They don't, and so if you want R to be able to do an ANOVA, you have to arrange it this way with them, with the groups underneath each other. And with a letter to say what group that person was in. Yeah, because R thinks in variables. Excel thinks in positions, right? The different things are in different spots in the Excel, but R thinks in subjects and variables. Right. Cool, so that's the setup. That's what it's for. Let's look at how it works. So if you were going to draw a picture of that data, you could imagine it this way. That these are the different groups you could have, and there's group A and group B and group C, and then this is the number that they get, and then every person could have a dot on this graph. So here's the scale that we measure the number on, and I'm just going to make up some data. So maybe the people in group A are spread out like this, and the people in group B are all like this, and the people in group C are all like this. How do you feel about this graph and what it means? Each person lines up with what group they're in. So this person 1 is in group A and they've got a number, and I draw a dot lining up with their number. And this person is also in group A and I draw a dot lining up with their number. And this person's in group B and I draw a dot lining up with their number. And all the people have a dot of their own. You don't draw any graphs like this in the course. I think there might have been an example one of these that the lecturer put in somewhere in one of the videos, but this is an idea. And this is a scatter plot, essentially. It's just traditionally with a scatter plot, you have numbers on this line here, but I've just put which group you're in instead. And so I can see, just from the way the dots are arranged, that the majority, that all of the people in group C are higher than all the people in group B. I can see that directly in my picture. And so I know already that my data is going to tell me that group C, that there is a difference between that which group you're in does make a difference to the number, because I can see it in my picture. Okay, I can see that the number is related to what group you're in. But it may be that I can't see that quite so clearly. Maybe my graph is more like this. And in this case, yes, it does seem likely that the C, there does make a difference because many of the C's are above many of the B's, but they do overlap really a lot. If I pick a random person from group C, quite a few of them are lower than a random person from group B. And so being in a different group doesn't guarantee that your number is higher. Right? Being in group C doesn't guarantee your score is higher than if you were in group B. And group A and B are almost the same, right? You're just as likely to have someone higher or lower than someone higher or lower here. And so how spread out they are and how mixed in together they are makes a difference to whether you decide that there's a difference or not. And so all of that has to be taken into account. So the word variance in the analysis of variance title is to do with how spread out each of the groups is. We're going to analyse how variable the numbers are in the three different groups and compare that variability, and hopefully if there's not much variation within the groups compared to how far apart they are, then I will conclude that yes, being in a different group does make a difference to your score. Whereas if there's a lot of variation within the groups compared to how far apart the groups are on average, then I'll conclude that maybe it doesn't really make a predictable difference. Like, that's the idea. I can't really make predictions based on this information because most of the A's are similar to most of the B's. How do we feel about what I've said there? Okay. So all hypothesis tests turn all these pictures and the numbers in the data into one final number. And that one final number, I have to imagine all of the numbers it could have been and compare what I got to all the things that could have happened. And that is the process of making a p-value. So ANOVA is no different other than the fact that there's a lot more data going on in ANOVA than there is in a t-test because there's three groups. And so I have to do an entirely different calculation. And I have to say, Fisher was an extremely clever person to have come up with this as a thing to do. It's quite remarkable that he could have imagined this thing. Because the t-test, the calculation you do is based on how far apart the averages are. And that kind of go, all right, yeah, I guess that makes sense. But the calculation you do in ANOVA is purely based entirely on variation. So, yeah. Okay. But the theory is the same. We're going to compare how far apart. Right, just wait. I'm going to draw this picture again. My other caveat is I'm making this up, right, because I didn't know what people wanted before we came, so I had no way to prepare. So bear with me sometimes, I will change track in the middle. Okay. So each of these groups has an average, a mean of their own. And if I treat it as one giant group, there is a grand total mean as well. Okay. So if I didn't know that there were three different groups and it was just a list of numbers, my best estimate for what one individual person could get is this grand total mean. Imagine that there are no separate groups, it's just one big group. This mean of the giant group is the best estimate I've got for what people might get in the future. I know it's going to be a bit up or a bit down, but that's the middle. Okay, and then each group has their own individual average. So I want to know if having a group average makes a difference to this. So maybe all the group averages are quite close to the grand average, and then I'm going, well, groups don't make much of a difference. That's the idea. And so the imagining that goes on here is that just statisticians, when they're thinking statistics, don't really think about people or chickens or petri dishes or whatever they are. They think about just a process that the universe uses to produce the number. And you go, okay, my imagining for the process that the universe uses to produce the number is that if there were no groups, the universe would just choose, we would have the grand mean, which is whatever it was going to be, and then everyone would get a bit up or a bit down, and that would be their actual number that they get. That's the idea behind it. And that is one universe. That's the universe where being in a different group doesn't make a difference. And the other universe is the one where, well, first, the universe says, which group are you in? Ah, you're in group A. Cool, 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 cool. In group A, you're going to have this mean, and you're going to be going up or down a little bit from there. And so the imagining in the second version of it is that what happens is that we have the grand mean, and then you go a bit away from that because you're in a different group, and then you go a bit up or down from that because it's just random stuff going on. That's the idea behind it, that to get to every person's individual score, so is the grand mean plus a bit to get to the what you need to get to the group mean plus randomness. I do not always write letters in words in the correct order the first time. Okay. All right. That's the idea behind what's going on. And what Fisher did is he said, okay, since everybody, when the universe calculates their number, is what has this bit for their local mean and this extra bit, I want to compare all of these bits for all the people to all of these bits for all the people and see which of them is bigger. And if there's more randomness than what you need to get from the grand mean to the group mean, then actually it's just random. But if it's the other way around, then the group mean does make a difference. That's my understanding of how the process works. And so he does all these things. Okay. So in order to calculate ANOVA by hand, which you do not do, and aren't we happy, you calculate the grand mean as if it was one giant group, and then you figure out how far everyone is from the grand mean, and you square them all and you add them all up. And so you get this most people call it SST. Do they use this SS terminology in this course? No? I don't know. That's okay, doesn't matter. What they do is they make this ANOVA table, right? And it goes something like, oh crap, just a second, bear with me. This is where it would be useful to look at the notes if we've got them. So in R, you'll type something like AOV. Is that how they do it? This is something I'd have to look up if someone had the notes handy. I don't have access to them, so I can't do that. Yep, and then you do something like the number twiddle the group, and you go data equals whatever the data was called. Yeah? Something like that? Cool. Oh, good. Yeah, like that. Cool. So the number is whatever the variable is that you're measuring on each individual. So do this and I can give you a computer back. Oh, and then you have to stick a summary out the front in order for it to get it to actually show you anything useful. Okay. Okay. So the reason I write my pictures the way I do is because this is a picture of this. This is my arrow that I draw here. Yeah. And so the way that R thinks is that you have the thing that you're trying to find out if it's different in the different groups, that measurement that you took, and then you put a twiddle, and then you put whatever it is that you think might be causing it to be, well, you can't do cause in statistics, might allow you to predict what this is. And then you have to tell it what the data is. And that's just a squiggle, by the way. You have to put the name of the data in that spot. And then, so that AOV, when you do that, R puts a list of different, creates a list of different numbers as results. There's like about 20 different things that it writes down. And then you have to write summary to get it to show that on the screen in a productive way. Yeah. So I just wanted to point that out. I think if you just don't do the summary, it will still work. But anyway, that's cool. And what it will produce is something like this. Come on. I dropped my phone last week and I haven't got a new one yet. It'll produce something like this. It'll say group or whatever the name of this thing is, and then it'll say residuals, and then there'll be a dash here, and it'll say DF, and it'll say sum square, and it'll say mean square, and it'll say F value, and then it'll say PR stuff. And there'll be all these numbers in these spots here. Like that. That's what it will produce. Something that looks like that. Cool. And in your exam, as far as I can tell, you obviously can't type R code. They will give you what the computer would produce and you have to interpret what it's doing. Yeah. So, right. Cool. Yep, go. That's a little later, but yes, it is coming, so remind me if I don't talk about it again. So I've just been asked about the Bonferroni correction. We will get there. So I will actually say it's worth pointing out that all hypothesis tests answer a yes or no question. And the yes or no question here is, does this appear to be related to this? So does being in a different group make a difference to the number that you get? And the answer will be either yes or no. Either it doesn't make a difference and all the groups are the same, or it does make a difference and at least one group is different to at least one other group, but you don't know which group is which. That's when the Bonferroni correction stuff comes in. Okay, so any other questions at this time about what I've been talking about? Okay, good. All right. So here's the thing. Now I have to start talking about the things that your statistician lecturers care about. So when you do a hypothesis test, which is what this is, you have to tell your statistician what the null hypothesis is. and you have to tell them what the alternative hypothesis is, and you have to tell them what the test statistic is, and what distribution it comes from, and other stuff. All good. So the null hypothesis is of the flavour. So you always say something along the lines of, let mu1, mu A be the mean outcome, or whatever the number is, in situation A, and mu B be blah 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 in situation B, and mu C be blah 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 in situation C. And you can either call them group A or group B or group C or whatever fits the context. And this part you always have to say. This part, just so you know, is called defining the parameters. Is that a phrase that you've heard? Like, define any parameters you use. That is what that bit is called, just so you know. Because officially in mathematics, you're not supposed to write any symbol down unless everybody knows what it means or you've told them what it means. So you're allowed to write like an F down because everyone knows it means an F statistic. But today you have to tell them what it means. So the null hypothesis is written as H0 or HO. And the null hypothesis is that all the means are the same. And you just put equals as for as many of them as there are. Or you can write it in words. You can say the mean is the same regardless of the group. Something like that. But this is the traditional way of writing it. And then the alternative hypothesis has to be written in words. You can't just put a not equal to in front of those, because it's possible to conclude that they're not all the same, even though two of them are, because the third one could be different. So it's totally okay for two to be equal and the other one to be different, and it would still break the null hypothesis. And so you would have to say, the means are not all equal. Yep. Do they use a small a here? Like they wrote HA? So there's really not any way of writing that with math symbols that doesn't take like 4 or 5 lines, so you just leave it as words. Okay. And then every hypothesis test has a test statistic, and the test statistic is F. For Fisher, named it after himself. Probably, yeah. The man who invented the t-test, his name is Gossett, and he won an award for his services to statistics. And he said, I wasn't that clever. Fisher would have figured it out eventually. Yeah. So, cool. And it is a complicated formula, so they don't usually write down that formula. But it is officially the mean square for the something. Have you got that page in the notes? I might look it up. Just bear with me. I want to make sure. We're just going to write it as an F. So this is one of the ones that you haven't been given an explicit formula for, because you're going to trust the computer to do all of that for you. Okay? F, and you might possibly say from the ANOVA table, just to make yourself, that is where it comes from when you go looking for that number. Okay, and the test statistic has a distribution. So whenever you do any hypothesis test, you calculate a single number from all of your data, and in today it's called F. And then you imagine if this was true, if it was true that before you collected the data that the universe's plan was for all of the groups to have the same mean, and any differences you see are just because of randomness. If it was true that all the group means should have been the same, how likely would it have been to get an F statistic this big compared to the one I've got? That's what you're going to ask the question of. I've got an F statistic, which is whatever the F statistic has worked out to be today. What are all the other F statistics that could have happened, and how likely are they? So that I can figure out how bad mine is compared to those. And so you say the distribution, if the null hypothesis is true, F is distributed according to an F distribution, and there will be two numbers in these positions here. They are called degrees of freedom. And these two degrees of freedom are listed in this ANOVA table under DF here. So the first number there, the top number is the one that goes first, and the bottom number is the one that goes second. But just to make sure that I tell you exactly how to calculate it, because you can figure these out without having the ANOVA table, this one is one less than the number of groups. And this one is the number of individuals total in the entire study minus the number of groups. I might do an example in a minute with proper numbers in the spots. And so these two numbers are what you need to look up the correct F distribution. There's a whole, your lecturer calls it a family. Every one of them is slightly different. So different amounts of data and different numbers of groups will all produce a different list of possible numbers for what the F could have been. And it looks like this. You don't have to draw this picture, but they tend to look like this. Like that. So this is the possible Fs that could have happened, and this height is how likely they are, and it's much more likely to have something that's small than it is to have something that's big. Like these are the small Fs here, that's 0 here, and these are all different values of F that could have been, and the small Fs are more likely than the other Fs, than the bigger Fs. Cool. The bigger your sample size is and the bigger the groups are, the further out this hump is before it starts to go down again. And officially, no one ever calculates this by hand because you can't. You have to get a computer to do that, like a normal distribution. You have to get a computer or a list of pre-calculated numbers to do the job because there's no formula for it. Binomial distribution's got a formula. These don't. Okay, and so what you do now is that your p-value will be the probability of getting, so you get this one and this is the F statistic from the data, and these are all the Fs that could have been, and this area here, that's the p-value. And R does all of that for you. And it puts it in this spot just here. tells you the F number, it tells you the degrees of freedom, and so theoretically if you knew how to find that area directly you could do it, but it calculates this all by itself. And now that it's a p-value, you can make the same decision you always make with a p-value no matter what situation it's in. The whole point of a p-value is to have a standard way of making decisions. And so now that it's a p-value, you can say, if the p-value is below whatever the level is, it's traditionally 0.05, but it doesn't have to be, then reject the null hypothesis and conclude that not all the means are the same. And if the p-value is above 0.05 or whatever number you've been told to use today, what does your lecturer use in this context? Retain or do not reject? Does anyone know what words they use for this? This is a difference between different courses. It's okay. Maybe retain? Question mark. Look it up. You are never wrong if you say do not reject. And so in this situation, the reason you're rejecting is you're saying that out of all of the F's that could have happened, if the null hypothesis was true, out of all the F's that could have happened, mine is pretty unlikely. And so I conclude that actually null hypothesis not true. And there is this one, whereas in this one you're saying, out of all the F statistics that could have happened, mine is, well, fairly common. And so null hypothesis could totally be true because I have got, what I saw here totally could have happened if it was true. So that's the reasoning behind it. It's this big proof by contradiction. The lower this number gets, the more evidence you have that the null hypothesis is not true. This is like the strength of your belief in the null hypothesis. Yep. Mm-hmm. Yep. Can I come and take a picture of that? It's the appropriate time to talk about it now, so thank you for asking. There's only like about 2 ways to say it. That's how probability is one of those things. It's really confusing. One word can make all the difference. And statisticians have worked out ways to say it that they declare are correct. And that is what they have. So let me take a photo of this and see what we've got. So I'm just going to take a little aside about p-values. Okay, so we reject the null hypothesis at the 5% significance level. Okay, that one is definitely true. So because my p-value is 0.01, and that has fallen below the 5% level, because that's 1% as a decimal, has fallen below the 5% level, and therefore I reject the null hypothesis. The lower the p-value is, the more strongly you disbelieve the null hypothesis. And so this one is true since 0.01 is less than 0.05, and that's 5% as a decimal. That's what I'm thinking at that point there. And that's a less than sign. The pointy end points to the smaller one. I might even put the words in. So definitely true. And that is a thing you're allowed to say. We reject the null hypothesis. All right, so that one's true. Next one. The probability that the null hypothesis is true is 0.01. All right, that one's bad. But this one's okay. This one is just not the truth. And so here's the thing. What a p-value is supposing, imagine that the null hypothesis is true. What's the probability of my test statistic? So it can't be the probability of the null hypothesis because we calculated it imagining already that the null hypothesis was true. So what if the null hypothesis was true? What would be the probability of this other thing after we imagined that the null hypothesis was true? And so it can't be the probability of null hypothesis because we ruled out thinking about whether that happened or not because we assumed it did happen. Is that all right? Yeah, because p-value is calculated based on imagining the H0 is true. Yeah, so it won't tell you a probability of H0 because we started imagining it was true. Yeah. This is why it's so confusing. So you're just not allowed to say this. It is definitely related to whether the null hypothesis is true or not, but in a technical sense, you can't say that. And the same thing is it won't tell you whether it won't tell you, so any statement about the null hypothesis, about the probability of the null hypothesis or the probability of the alternative hypothesis is always not valid. You just can't say it. And the other thing to know is that in statistics, you never know if the null hypothesis is really true or not. You never know for sure. But even you never even know the probability of it, at least in this kind of statistics. So there are other kinds of statistics that you're allowed to say that sort of thing. And so all of the ones like the probability that any hypothesis is true is any number. You can't say that at all. It doesn't matter what hypothesis it is. It doesn't matter what the number is. If you're interpreting a p-value as the probability that a hypothesis is true or false, you're not allowed to say it because it's all a big imagining what if that you're calculating here. Is that okay? Yeah. But you're allowed to reject or retain it because we're saying, well, even though we can't say that the probability is 0.01 for the null hypothesis, I was able to produce a low probability when the null hypothesis was true, and so I don't believe it. Yeah, it's a fine line that we're walking here. But ultimately, this is what is not acceptable in this area of statistics. We okay? Okay, so that's how ANOVA works at the first step. And then after you've rejected the null hypothesis, then you have to decide which group is different to which group. So if you don't reject the null hypothesis, you just stop. So stop, that's the end. You've conclude you conclude that the mean in all the groups is the same, and so the group does not, the number outcome is not related to which group you're in. There are lots of ways of saying that. You might say the number outcome is not related to which group, or you can't predict the number outcome from the group, or the group means of all the groups are different, all the groups are the same. You do whatever's in context. So if the context was, does feed make a difference to chick weight, you would say feed does not make a difference to chick weight. Okay, but if you do reject H0, then you have to find out which group is different to which group. And this is where you follow up with more t-tests, with the Bonferroni correction thingy. Now, I don't know how it's done in this course. Each course does it differently. Can you tell me, is there a thing after that? How do you do the Bonferroni bit? So the people who do the videos, there's like lots of different people in the videos, or is it all Sanjeeva? Mel? Yeah. Just checking. Oh, okay. That's very all right. So you follow up with some sort of post hoc test is what they call it in medicine. I don't know what they call it here. It wasn't called post hoc there, but you follow up with more tests to compare the different groups to each other. And the one that was on your screen there that they asked R to do was the Tukey's honestly significant difference test. So in R, they wrote Tukey HSD, and then you put the ANOVA inside it. So there's two things. You've got the ANOVA, you can do the summary and it tells you the original thing, and you've got this Tukey's HSD. So Tukey is the man who invented the box plot, by the way, in case you're wondering. That's that guy. I think he's still alive, actually. He invented the box plot in 1977. It's quite recent in statistics. And he also invented this thing called the honestly significant difference, as opposed to just significant difference. And what it will do is if you ask the computer to do this, it will give you a big table and it will say each group compared to each other group, and it will give you a confidence interval for the difference. I'll tell you what the difference is, and it will give you a p-value for each one. And then if this p-value is under 0.05, you'll conclude that these two are different. If this p-value is under 0.05, you'll include these are different. But if this one's above the 0.05, you'll include that this one's not different. And so there may be any combination of them having above or below 0.05s. That's how it works. And it can be extremely difficult to interpret what this means. I warn you, because what will happen is that sometimes what will happen is that if you imagine the means, if it was like this, the A, B and the C, what it might say is that there's no difference between A and B because they're really close together, and there's no difference between B and C because they're really close together, but it will say there's a difference between A and C because they're not that close together. And so it might seem to, if these are the same and these are the same, logic would dictate that these are the same, but that's not how it works. If you're not saying they're the same, you're just saying they're close. So it can be really confusing to interpret the outcome. But what this would be saying is that if you want to have a difference, you're going to have to switch from A to C. Switching from A to B isn't going to be observably different, but switching from A to C will be. So, yeah. The reason I say that is I had some students in the second year Foundations in Plant Science course, and they had to do this, and they're going, what does this mean? It's like, yeah, it's just confusing. You're just going to have to figure out what you want to say and focus on the one that's important to you. Yeah. And so, yeah, this would have had, maybe this would have been like 0.63, 0.06, and this one would have come out as 0.03, and this one would have come out as 0.07 or something. And we'd say that B and C aren't different, and A and B aren't different, but A and C are. Yeah. And what it has done, what Tukey's honestly significant difference has done, is it has adjusted these p-values and made them a bit bigger than they should have been. Yeah. And Bonferroni's correction is different to that. It has a different way of bumping them up, and the calculation is in the notes there. So this is Tukey's correction. So I'm just going to say, so these p-values have been gotten from t-tests. So what they've done is they've said, okay, well, I want to compare these two groups, that's a t-test. I want to compare those two groups, that's a t-test. I want to compare those two groups, that's a t-test. and they've done 3 different t-tests, but they've made the p-values just a little bit bigger so it's harder to find differences accidentally. I'm pretty sure that Bonferroni's correction is that you think you multiply the p-value by how many different comparisons there are. So we've got 3 different comparisons. If there were 4 groups, we would have had A, B, and A, B, and A, C, and A, D, and B, C, and B, D, and C, D. There would have been 6, and we would have multiplied them all by 6. Yeah, but you'd have to look that up. So these have been adjusted by Tukey's method, but Bonferroni's method is a different method again. I can never remember if it's 2 R's and 1 N or 2 N's and 1 R. And these adjustment methods, if ever anyone asks you why do you do them, it is to control the type 1 error rate for multiple comparisons. They've talked about type 1 error, haven't they? Some people don't do that adjustment afterwards, because the philosophy is that, well, I would have stopped if my first ANOVA came out as not significant, and so I'm already dealing with those multiple comparisons by doing ANOVA first. But some people, well, it's been going on for long enough now that people just expect you to do it. So, yeah. How are we feeling about ANOVA? That's the idea behind it, and they're all the details. Yeah, so just going to do something. Why is R not there? Yeah, open. Well, if R opens, then I will do something. It's being annoying today. Oh, no, we've got a spinning hoop. All right, I was just going to try and make R do one. No. My computer is being annoying. Okay, I give up. Oh. Oh, wow. That's weird. All right. that's what R looks like traditionally to you? Is that the help is on for some reason? And I would have to... R hasn't actually started. All right, it's just being annoying. I'm just going to have to stop. For some reason, my computer has decided it doesn't like R today. Luckily, you don't have to use R live in the exam. All right, anyway, would have been nice. Cool. So the only other thing that you need to worry about with ANOVA is that all hypothesis tests have assumptions, in inverted commas, that you have to check. And the reason they have assumptions is that because you're going to calculate a probability, basically, you can't calculate any probability without making some assumptions. Even when you roll a die and you say, oh, the probability of getting a 4 is 1 in 6, you're making the assumptions that all of them are equally likely. And so all probabilities have assumptions to go with them. And in order to get this nice little curve here that tells me what the p-value is, I have to make some assumptions about where the data came from. And the assumptions for ANOVA are, there's independence assumptions, which you can't check from the data. So the values are independent within groups, and the values are independent between groups. And you can't check that from the data itself. That can only be done by basically randomizing people to the groups, essentially. So you check both of these. The story of how the data was collected. So if all the people in group A came from the same family, then you would probably assume that they weren't independent, for example. But there are two assumptions that aren't about independence, but are about how the data originally, the distribution the data originally came from. And they are that every group is normally distributed. From a normal distribution in every group, and you check that with a QQ plot for every group. That's what they use, QQ plot? Yeah, QQ. QQ plot. QQ plot for every group. And if they're all close to the reference line, they follow the reference line, then they're all normal. Check with QQ plot for every group. So when someone asks you to check an assumption, you're supposed to say where, if it's not the story, you're supposed to say where you looked, what you saw, and what your conclusion was. So I would say, for example, I would say in the QQ plots, everyone The dots are close to the reference line. So the normality assumption is reasonable. Something like that. And it's totally okay to just repeat sentences like that and not make up new ones every time. Because as we said earlier, sometimes if you say it a different way, it's just wrong. Theoretically, there should be several ways of saying it that are both grammatically and statistically correct, but sometimes they're just wrong. And so I've said where I looked, what I saw, and what my conclusion was. And when you're assessing assumptions, you normally conclude whether they are reasonable or unreasonable. That's usually the word that you use. You could possibly use the word valid, but reasonable is more less forceful. So, and there's one more assumption, which is that the variance is the same in each group. And the way you check that is the biggest variance has to be less, no, the biggest standard deviation has to be less than twice the smallest standard deviation. So standard deviation divided by the smallest standard deviation has to be less than 2. So I just want to do a proper example of that. Suppose in group A and group B and group C, you had the standard deviations were like 1.8 and 2.7, not 2. Yeah, and 2.1. So what you do is you take the biggest one, which is 2.7, and divide it by the smallest one, which is 1.8. Oh, damn it. Big is not a fancy word. It doesn't sound formal enough. Largest standard deviation divided by smallest standard deviation is 2.7 divided by 1.8. And when I get my calculator to do that, well, 1.8 times 2 would have been 3.6, so it's going to come out to be less than 2. But just for completeness' sake, oh, exactly 1.5, cool, which is less than 2. Less than 2, so the equality of variances assumption is reasonable. But if this had been like 3.7, then it wouldn't have been reasonable, because 3.7 divided by 1.8 is just a little bit more than 2. There you go. That's what it is. Other courses, if you Google online how to check that assumption, they'll sometimes give you other things. There's a whole hypothesis test you can do. This is actually a hypothesis test as well. It's just that the number 2 is the value that gets you from bigger or smaller than 0.05. So quite interesting. This is a also an F test. So kind of cool actually. But anyway, the point is that even if the standard deviations weren't the same, it would still probably be okay. A lot of these hypothesis tests, even though they're based on certain assumptions, will be fine anyway. Something, especially with the variances one, not the variances, especially with the normality one, if it's not normal, but you've got like a 50 in every group, it'll be fine. And you're not going to base your entire decision on just the p-value anyway. You're going to say, well, base it on the p-value, and now we're going to look at how much difference it makes. And so in real practice, it's okay. But there are things to do. in real practice, if it really is highly non-normal, you'll do a whole different thing instead. You'll do the Kruskal-Wallis test. And Kruskal and Wallis invented it at some point. Most of the more recent tests are named after people. The older ones just have generic names, even though people invented them. But, we're a lot more into referencing correctly now than they were 100 years ago when they first started inventing these things. Okay, cool. So officially, you're supposed to do all these things before you do the ANOVA, and then if they don't work, you're supposed to do something else. But usually in exams and assignments for a course like this, you do the whole ANOVA and then you check the assumptions at the end. But officially, you're supposed to do it first. Yeah. And in an exam, what they'd do is they'd give you all those QQ plots and ask and say, say, for your interest, here are some plots that you may be interested in referring to. And so you'll say, I refer to the QQ plots for each group, and I saw this, and this is what I concluded. Yeah. And there's a classic where you conclude it's not normal based on the QQ plot because there's a distinct curvature. And then they say, is this a problem? And you say, no, because the sample size was large, so the central limit theorem says that we can still do, that the normality assumption isn't needed, something like that. So, then the assumption isn't reasonable, but I don't know how you even say it. It's still okay to use the hypothesis test anyway, but I'm not sure how to do that, because reasonable is the word I would use in that context. Using the allowed? Using the test is still allowed? Valid? Valid. Let's use valid. Then the test is still valid by the central limit theorem. That's a sort of response that you could be giving to a question like that. But if the sample size was small, like only 10 each group, then you'd probably say, no, we should do a different test. But you don't have to specify which one because they haven't taught you which one in this course. Yeah. They usually ask quite leading questions in these exams. They're trying very hard to make sure that you pass. Okay. How are you feeling? Good. Any other questions or thoughts about ANOVA? Oh, out of interest, just while I'm at it, what sorts of graphs would they draw? They probably draw a box plot for each group, don't they? Is it good? So the traditional graph would be like this sort of thing, right? Is that sort of the graph that you would expect to see? Yeah. Yeah. Just thought I should put that in because the box plots are fine, but I find the dot version is easier for me to process what it's doing. Yeah. And box plots are not that easy to interpret if you don't know what they mean already. They're only invented in the 70s. Only 2 years before I was born were they invented, and I count that as recent. Yeah. Okay. ANOVA is one of the ones that is traditionally difficult for people to process because the computer pretty much has to do the whole thing. But even the ones that you can do by hand, there's just, a lot going on. It's weird because statisticians are actually really into drawing pictures. They're really into visualizing the data, but it's weird that it just hasn't come up as often as it could have. Yeah. I'm obsessed with drawing these pictures. I do it with all my medical students and all my science, Everyone's got like a research methods in or introduction to research in insert topic here. And they all come to me, and so I have to help them decide which stats goes with what. And so, that's what I do. Because, I remember my very first day as Maths Learning Centre coordinator. My predecessor, we had one day in common to do Passover, and he literally was walking out the door, and he turned it round and said, "Oh yes, the medical students will be arriving soon," and left. And okay, and it was a very interesting time because they don't even do a stats course. They're just asked to interpret statistics in research articles. So poor things. I would not want to do a medicine degree. If you're planning to do one later, then more power to you, and please come to the Maths Learning Centre when you do your statistics. But it's a big commitment because it's a 6-year degree. It's a big commitment, and they have a lot of exams. All right, well, let me talk about that confidence intervals and prediction intervals since it was one of the questions we had. Okay. The ultimate goal of any statistics is usually to predict things. Even though we spend a lot of time asking yes or no questions of, is this related to this? The goal is usually to try and predict things. To say, even in this situation, it's like, can I, from knowing which group they're in, predict what the outcome is going to be? And with regression, that's this picture. Everyone's got their own number, and you try and predict based on this number what that number is going to be. So maybe I've got temperature for my people, and I've got number of milligrams of chili in the meal, and that's what I'm going to do. I'm going to see whether they make a difference. Maybe it does, maybe it doesn't, who cares? It's just a pretend example. And you would draw a graph something like this, and this would be the number of milligrams of chili, and this would be the temperature, and everyone would have their own dot. And it would line up with whatever the number of milligrams of chili is here, and this person has that temperature, and this might be like 35 degrees, and this is 38 degrees, something like that, right? They don't have to go all the way to the bottom when you do a scatter plot. You get to choose what kind of story you plan to tell. Okay, and this is great, but they're never going to be perfectly on a straight line. And so the idea is that if I know how many grams of chili, milligrams of chili we had, so maybe it was like, 50 milligrams of chili or something. Because chili is pretty light, right? Okay, cool. That'll do. I know that there's all these different dots here. That 50 milligrams of chili is not going to exactly tell you what the temperature is of a person who ate that meal. Not exactly, because they're all a bit random. And the idea of how regression works is that we imagine that the universe, when it chooses someone's temperature after they've eaten a meal with chili, that it goes, how many milligrams of chili were there in there? Cool, I'll do this calculation and it will tell me where the line of best fit is, and then I'll add a little bit of random bit on top and bottom. That's the idea of the thing. And so you have something like, do they call it Y and X and stuff? And do they use beta or B? Yeah. Some lecturers use B instead of beta. They mean the same thing. And there'll be some numbers there that do this thing. And so maybe this is like 20 and this is 80. I'm just going to make a guess. Let me have my slope. That's 2 there, divided by 40 there, which is 1 in 20. So and coming back in. Here's it about. About 34, something like that. Okay, this is my pretend thing. And if you do it in a computer, it'll all have more decimal places than that. It'll be like 34.18 and like 0.0517, something like that in the calc computer. And this is the fitted regression line. This is the estimated regression line. And so from this, if I had 50 milligrams, I could put it into this formula and it would tell me approximately what temperature I expect. That's the idea. So I would say something like, for 50 milligrams of chili, we expect on average a temperature of 34.18 plus 0.0517 times 50. $36.7565. I've probably made my estimate of temperature too low, but that's not too far from 37. These people are pretty cold. That's okay. But we know two things. Even if this was the exact correct mean that all people with 50 milligrams of chili in their meal, if we knew this was the exact average temperature that everybody who has 50 grams has, they won't all be the same. And there'll be a little bit up and down on both sides. This we know to be true. But we also know that this is just one collection of data I could have had. If I did this experiment again with another group of people, I would have gotten a slightly different line of best fit. And that line would have had a slightly different slope. And so not only would the individual people be different, I would have had a different calculation here in the first place. And so this number could have been, the number for the mean could have been lots of different things. Right. And so I want a confidence interval for what the mean could be. And then I also want to know, well, that's what the mean is. How spread out are the actual individual people? That's the question. So just looking at this 50 here, if this is where the means could be, possible means in all the other possible data that I could have collected, it's all very could have, should have, would have in statistics. And then each of those means, the people would be spread out around that if I had all those different means. And so these are now the possible individual temperatures. So this green one, that is the prediction interval, and this one is the confidence interval for the mean. And this is the prediction interval. And that is why the prediction interval is wider, because the confidence interval is trying to cover just where the mean is for the people of that, in that group, and the prediction interval is trying to cover all the possible people. Well, 95% of the possible people. Does that answer the question? Yeah. I can't remember the formulas for them. There's like, one of them's got a 1 plus under the square root and the other one's got something else. But yes, that is what's going on. And so every position along the line of best fit has its own little confidence interval and its own little prediction interval, and they'll all be slightly different based on things. And they tend to be wider at the edges than they are in the middle, because you've usually got less data at the edge as well. That's why prediction intervals are wider, because they're covering the individuals, not just their average. Yeah. So individual values, not just the mean. Yeah. Cool. That would be, I think, an acceptable answer if someone said, why are prediction intervals wider? Right. Oh, it's really guesswork for a stats exam to try and guess the ways that you might say things when you get there. It's really important to do what you've done, to ask about this sort of stuff so that you can imagine what you would say, so you don't have to make it up when you get there. A little bit like writing a creative writing exam in English. You don't want to make up the story from scratch in the exam. You want to have a few options for general storylines that you might be able to use, and it's a similar thing in statistics. Do they still do creative writing exams in English? I don't know. I had one when I did my English in year 12. Sorry? I deeply hated my English teacher in year 12. Cool. Sad. Well, probably good. No, it's not sad at all. I'm very happy for them. No one should have to do exams. You could say they're a necessary evil, but I think they're just an evil. But anyway, here we are. Yeah. Or like when people go for interviews at Google and whatever, and they have to do those creative thinking problems, you want to have some thoughts to begin with if you can. Yeah. Luckily in statistics, you can reuse the same sentence frames and put the appropriate words in the right spots. Yeah. Well, got 10 minutes to go. Any other questions? All good? What about people in the Zoom? Whoa, man, what's going on? Okay. Oh, good. Well, I'm going to stop the recording then.